Hello and welcome to this very special episode for Electromaker. I'm your host, Robin Mitchell. In today's episode, we're going to be building the Lego Maker Planetarium that combines the best parts of the Lego Planetarium kit, along with a Nema 17 motor and the Arduino Nano 33 IoT. And then a smartphone so then you can control it with your voice. So a voice-controlled Lego Planetarium kit that combines the best of Lego with electronics. So let's see how we do it. So the purpose of this project was to take the Lego Planetarium and give it a bit more spice. So I thought the best thing to do is to add electronics to it. And what better way than to control the input shaft to the planetarium via a motor? So normally when you build the Lego Planetarium, you get a little crankshaft and you can turn that, and as you turn that, the entire thing moves. The Earth moves, the moon moves, the sun moves, the whole thing moves around the sun. So it's really quite a cool representation of how the Earth and the moon go around the sun. And it even represents the seasons with the angle here, and it actually rotates. So you do get accurate seasons, moon phases, and the days as the thing rotates. Now, while this is really cool, it's also a little boring in my opinion, because being an electronic engineer, I like to add some stuff to things to make them a bit more interesting. And one idea I had was to make this whole thing voice activated. So I could say go forward 10 days and the whole thing would then move 10 days. And if I say go back 10 weeks, it would then reverse 10 weeks. Now the core part of this project is the Arduino Nano IoT 33, which sits inside this little enclosure right here. Now all this is doing is running a web server, and whenever you connect to that web server, it gives you a website that it hosts on itself. Now the only problem is I couldn't actually embed the CSS or the JavaScript. I'm not quite sure why that was the case. Something tells me it might have been there must have been some weird character encoding, so when I tried to save it into the C file on the actual program, it wouldn't do it. So to get around this mess, what I kind of did was cheat a little bit, and I hosted some of the core files on my own server. So if you look in the source code, you'll see my website link and you'll see where it's stored, and basically whenever you load the website that this thing delivers, it pulls some of the CSS and JavaScript from that. But by doing that, we can keep the HTML running on the Nano IoT 33 really simple, which is great, and so it's also easy to maintain. Now on the front of this enclosure, you'll see that we have a 16:2 LCD. Now this display tells us what's going on, and if you look there very closely, you can see that it still has its plastic on. So just for you guys, I'm going to peel that off right now. Watch this magic. Wait for it, wait for it, wait for it. This is not, I've had this for years and it's going to be peeled now. Oh, peeled. Nice. So this enclosure contains a breadboard with the Nano IoT 33, along with a stepper driver chip, which is basically the A4988. Now this chip is very famous. You can buy it almost anywhere, and this little driver board has some pins on the side. It goes straight into a breadboard, and all you have to do is connect a few of the signals up, the step and the dir, which are the direction of the step, and they basically tell how the motor to move and which direction to move. And then you've also got some other pins like enable and the micro stepping, but we're not going to worry too much about that right now. The only thing that matters is that the Nano IoT 33 is controlling that stepper motor driver, and then that stepper motor driver is driving this Nema 17 motor, which is directly connected to the shaft of the planetarium. Now, in order to get the shaft to connect to the planetarium, I had to do something a bit unforgivable, which was literally cutting a piece of Lego using a pair of snips. But I promise you that it was worth doing, because it had then allowed me to connect that Lego piece into this coupler here, which then goes into the motor. Now, the coupler is quite interesting because it's like a springy one. So the two shafts that it connects to can actually be at different sort of like axes, and then it will still transfer the torque across from the first shaft to the second. So I can give it a little bit of wiggle like this, and you can see it would still turn it and they're still connected. So it doesn't break it, and it gives it a bit of flexibility. So as you can see, that gets the motor connected to the planetarium, and as the motor turns, as you see here, the planetarium starts to rotate. Now, when I first started this project, I was really hoping to use these dot matrix displays that have a row of, I think, 8x8 or 7x7 LEDs. I think it's 8x8. Yeah, it's 8x8 LEDs. And then you have multiple modules, and then you can stack those modules, and I've got loads of them. And I was really hoping to have a nice big matrix display with all the dates and stuff, and it would look really cool. Sadly, these, they don't work the way that they claim, and I just could not get them to work on the Arduino Nano boards, no matter what I tried. Then I had another idea. Why not go a bit bigger. And I thought this display would be really cool. I've already used it before with the Mega 328 something, the much bigger one, the Arduino Mega. And I've already used it a lot of times, so I know that it works. And as cool as it is, and as amazing as it looks, when I plugged it into the ESP32...
And it exploded.
Why that happened, I'm not quite sure. Maybe I forgot what wires did what. To be fair, I was a bit of an idiot and I wasn't really double checking what I was doing, so I was kind of just doing the project quite quickly. I think I pressed two wires together that shouldn't have been touching, and then it popped basically. And unfortunately, I've now lost my ESP32 Arduino Nano board, which was fantastic. But luckily for me, Richard gave me some free stuff, and I had the Arduino IoT 33 lying around, and I also had one of these LCD displays, which is I2C. So it was a lot easier to use, and the libraries are trivial for them. Now, there's only one problem I'll say that this project has, and it relates to the Planetarium itself. Now, there's nothing wrong with the Planetarium as a kit. In fact, I'm surprised how accurate it is. With the input crank, 3 turns on the crank does about 1 day on the Earth, and it does actually spin about 1 day. And, you know, if you're doing 365.25 days or so, it does orbit the whole thing. So it's actually surprisingly accurate. The issue is that, and I think it comes down to the fact that it's plastic, but when you turn the crank, you'll find that sometimes I think that there are so many gears connected and there's so much sort of like load on these cogs, it's kind of hard for it to drive it. So sometimes you'll drive a bit and nothing will happen. And then suddenly, as you saw there, it's already turning by itself, because I imagine there's some sort of twisting forces in the axles. So that power doesn't quite get transferred until maybe some small amount of force is overcome. And it also means there's a bit of backlash as well. So if I start turning left, I'm turning left and right here, and it's basically doing absolutely nothing. But that should already start rotating, because if I then go forward and go a little tiny turn, you actually get turns. So there's a bit of backlash, and I think there's a bit of skewing in those axles. But besides that, this kit is surprisingly accurate, and it is really, really cool. So my first attempt at printing the case sort of worked, but is also horrendously ugly. We've got all kinds of nasty bits of stuff here and there. And if we just get a zoom in on this and bring this here, and let's get that actually in focus. It's all manual focus these days. Yeah, so as we can see here, this is the case we first printed. It looks horrible. I mean, well, structurally it's actually very strong, but it looks pretty nasty. And it turns out that my printing head had some weird plastic leaking out of it, and I think it's because it hasn't been used in a long time. It needs to be cleaned up, so I had to service the whole thing. And then once we had got that done, then we got ourselves a much nicer looking case, as we can see here. Much better. So we've got 2 different prints that we tried. We used the Ender 3 and we used the Anycubic Cobra 2. Now the Anycubic Cobra 2 prints at about 3 times the speed of the Ender 3. I think it's about 150 millimeters per second compared to these 50 millimeters per second that I use in the Ender 3. However, you might be thinking, okay, let's use the Anycubic Cobra 2. Except for the fact that sometimes the print quality can be a bit rough and not great. Whereas we look at the Ender 3, it's, you know, absolutely fantastic. So this is the one we're going to use. Plus I quite like the white anyway. But that is going to be our enclosure. And then what we'll do is we'll just go ahead and stick the breadboard inside. We'll glue on the display on the front with some hot glue. Get the USB cable in the, get the USB cable and the motor cables coming out the side, and then that will be our project enclosure. Now, when I attach this display to this case, I'm going to use a little bit of hot glue, do it from the back side here, pop it on the sides, and because of that, mainly because of the clearance between these pins for I2C and the wall, I'm going to manually solder those to the connectors here, and then use little wires to then go into the breadboard, which will then be stuck on the bottom. It's also kind of important to make sure that you remember which pins do what. In this case, we've got ground, VDD, then we've got SDA, then SCL. So remember that before you solder this thing up. So I know that I could spend all day trying to design the perfect enclosure for this display, but you know, time is of the essence, and we really just want to get this thing working and enclosed so it all looks a bit pretty. So the best way for me to glue this in is actually not to try and figure out how to do it like that, but instead place it down flat. That way it will be perfectly level on the other side. Pop some glue in on the sides, and that's going to look great. And then once that's done, we can go ahead and take the sticky part off the back of our breadboard, stick that in, the cable goes through the side, and then we're going to solder those little pin headers to this board via some wires. Isn't it? Blimey. Really underestimate how sticky these things are. Right, so now we're going to really shove that in. And the degree of precision on this is so stupid because like it's literally on the edge. So I'm going to have no choice but to cut off my breadboard's side pieces. Probably do a little bit. We can probably do a better job of that actually. Let's go in a bit more. There we go. Yeah. Which now means, in theory, this, once we connect those up and get ourselves a power cable coming out for the motor, in theory, this should all fit together quite nicely like that. So that gets us this nice little display. We've got our board inside there, and the enclosure will fit smoothly over our thing, which is very, very nice. So now I've got to get the, what's it called, the motor connector in. And I'm just going to pop it out of the motor for a second. I'm going to feed it through here, making sure I give myself plenty of space for the USB cable. With my hot glue gun, just go blonk like that. Honestly, I swear to God, this is the crime of the century. Watch me make breadboards permanent. You're not really supposed to do this, but you know what? It's gonna work. It's gonna work. And now I'm going to use my Mitchell Electronics traffic light PCB, only $9.99, as the thing I'm going to use to kind of like hold it in place while the glue dries. So now I've got to go and power this thing up and just make sure I've got the wires the right way round. So I'm going to need to get myself a micro USB connector. I was about to call it a micro USB-B, but it's not, it's just a micro USB. So let's go find one. Plug that in. Yep, there we go. Nice. Okay, got it. So now that we've looked at the hardware overview of this thing, let's jump over to the software to see how that works. So our Planetarium uses the Arduino Nano 33 IoT, so naturally we're going to program it in the Arduino IDE. It's a fantastic IDE, provides all the libraries I'm going to possibly need for this project, which makes this whole thing so easy to do. For example, we've got the Wi-Fi Nema library that lets us connect to Wi-Fi so easily with like three different functions. We've got the wire library, and that's going to be used to communicate the LCD with our Arduino. And then we've got the Arduino JSON library, which is great for handling data between clients and servers. And then, of course, we've got the website H. And what this is basically is just an include file that has all of our HTML code. Now, I'm not going to go through the whole list of code because it's absolutely massive. It became a lot bigger than I had originally anticipated. But really, the only thing that matters here are that when we basically start up in the setup function, you know, we start the UART port so we can do some debugging. We set the pin mode so that we can control the motor. We then enable the LCD and initialize it. We connect to the Wi-Fi, and then we open up a server. And then from there, we then listen into connections that come in from clients. Now, when a client does connect, what they get is the data held in this string, which actually is the homepage HTML. So we've actually written that in VS Code because VS Code is absolutely fantastic. Now, of course, you can't copy and paste this into C. So you'll have to find an online tool to strip out all the spaces and all the possible characters that might cause you problems, which is probably why I couldn't incorporate the CSS file, because the CSS file is humongous, as I did copy an example online to get the scrolling stars parallax. So there's a lot of stuff here. So instead, I host these two files, the script for the whole app and the CSS on my server locally, so that when you actually load this web page from the Arduino device, you have these two pieces of code here that tell your device, your smartphone, sorry, to basically grab the script and the style from a remote location. Now, of course, this code is also looking for post requests. So if we do detect a post request, we try and basically pass that request, and we figure out, is it days, months, or weeks we want to change it by, in which direction, and how many. And that's what this code's doing. And once it's figured it out, we come down here, and there's a whole bunch of different code, including updating motors, And then we also have the actual going forward and going backwards. So the way these work is it just keeps adding days until it gets to the date it wants. And to be clear, increment day and decrement day are used to control what the day is going to be depending on if you're subtracting or adding to it, and it will account for things like leap years and the direction that you're going. And the going forward and going backward are actually different. That's controlling the motor with respect to the day. So the two work independently, so the actual motor can keep working while still receiving commands. And it also means we have a nice little animation whereby the closer it gets to the day, it slows down. Now, to get speech recognition to work in this project, instead of trying to do it on the Arduino, I've instead taken advantage of the speech recognition module in JavaScript. So our browser is actually handling that complex task. Now, if we go back to the HTML file, you see we have a speak button. And when we click that button, we're going to call this function called speak toggle. So that's going to switch between listening and not listening. Now, when you do toggle that button, you can see here that there's two different functions that we can do: recognition start and recognition stop. Now, the cool thing is that when you start the recognition, it will automatically complete when it no longer hears you're saying something. And when that happens, we go up here to the recognition.onResult function. And what that will do is it will return the transcript as a string, and then all we have to do is split that string into the individual words that I said, and then we determine what those words were. So the first word will always be the command, which is forward or back. The second command is the number, which is going to be the number of something that we want it to change by, whether it's days, weeks, or months. So in this case, 10 days, 10 weeks, 10 months. And then the third parameter is the time unit, whether that is days, months, or weeks. Once we've successfully passed the parameters, we call the appropriate function, which does a post request to our server on the Arduino with the data. Okay, I've got the app up. We're going to do the first test and see if this whole thing works. We've got the motor powered, we've got the little controller powered, we've got the app up. Let's see if it works. So start command, and we're going to go, let's say, forward by, let's say, 30 days. Allow. Forward 30 days. Oh, that's fantastic. And it even worked. It actually came about 30 days, so very nicely. The direction was the wrong way around, but we can fix that. But hey, it's working. Okay, so I've just finished doing some programming and mechanical adjustments. The first thing I did was change the amount of current going into the motor to make sure it doesn't stall. I've also added a bit of oil into the gears with mixed results, but we'll see. And I've also changed the code so that it turns the right way. So it's just doing its boot sequence. Once it's finished, we'll start playing with the system. And I'm going to quickly just tell it to not go the full 6 months ahead that it does when it boots up, just to test the motors. It is still syncing time. There we go. So let's go ahead and just quickly stop that by going back 100 days. And yep, that's done the job very nicely. So once it stops, we can then start playing around with it. So let's start by going forward. Forward 10 weeks. I love how it does the slowdown. It's very, very nice. Now let's try going backwards. Back 10 weeks. This is working really nicely. Fantastic. Now let's try a quick experiment. If I tell it to go forward by 10 months, in theory it should go back by 2 because that's the quickest direction to get to it. So let's see if that works. Forward 10 months. Ah, yes, it's going backwards. Yes, and slowing down, which is actually correct. So that's really cool. So it is finding the quickest way to get to its point. So that would be 2 months from where it was in the past, because that's actually 10 months in the future. So it always tries to find the quickest way to get round. Very nice. And just for good measure, forward 365 days. Oh, it's not going to move at all because it's already there, of course. How funny. So if you like what we do here at Electromaker and want to show your support, then head over to the Electromaker store where you can find all the bits and bobs you'll ever need for your next weird and wonderful project. This is Robert Mitchell, signing off.